students and researchers at UNSW. We also can partner with particular units for a day a week or a contract and things like that. We can take on small projects. And what else do we do? And we run short courses and we review grants. So we do a lot of stuff. Be aware of what we do and get in touch with us if you want. I think that's all I've got to say. Over to Liz.
Thank you. So I'm gonna start sharing my screen. I think this is the one, the other one. No, why isn't it working here? There it is. Okay, so thanks. And the title of my talk is It All Depends, Analyzing Dependent Observations. And if you have any questions, feel free to raise your hand or, I don't know, something, maybe people that are online, so that I know if you have questions. And so the outline, this is the outline. How do we start a research project? I'm going to mention some basic, simplest models. Then what happens when, well, observations are independent, then I'm going to have an example. I'm going to have an example of when we have two observations in a cluster, in a group, then when we have groups or clusters with more than one observation, and then I'm going to mention what happens when cluster matters, instances of non-independence, things to consider, and a disclaimer at the end. So how do we start a research question? How do I get rid of this thing on the top?
I didn't know how to do it last.
Okay.
Yes.
Go to the street of and it's hide floating.
Where is it? Loading media. Okay, perfect. Thank you. So how do we start a research project? So in this case, where is it? It's scrolling now down. Is that working?
The blank screen.
No. Yes, we'll have to do that, I guess. No. Sorry about that, but this is the okay. So nice.
So left, right works.
Okay.
You can
So-
probably hide those.
I think so. Hopefully it's worked now. So we have a research question, and many times is there an association between variable X and variable Y? Now it's not working anymore.
Yeah, I think you need to keep it.
The other, right? The other, where was it? Okay, so we also, well, we have a research question, and then we have to see if we have to collect the data or the data already available. What's our population under study? Are the subjects and outcomes independent? And then the outcome variable type, is it numerical, categorical? Because the analysis depends on the variable type, right? On the outcome variable type. And does it only depend on the outcome variable type? That's what I'm going to be talking about today. Now, some basic simplest models that we have, when we have this big assumption of observations are independent, we have, and I think many of you have seen the one sample t-test, two sample t-test, linear regression, and chi-square test, right? So a lot of people have used this in their life, but a big assumption about this test is the observations are independent. Now, let's say that we have these observations scattered around, but they belong to only one group or one cluster. So in that case, what we can use the techniques, depends on the research question, depends on the outcome. We can use one sample t-test, two sample t-test, etc., etc. Now, what happens if we have then two observations that are really, really close to each other, that they belong either to a group or a cluster? then we don't have that idea of being independent. So the techniques that we've seen before, well, that are more common, the t-test, the chi-square test, should we use them or shouldn't we use them, since the big assumption is they have to be independent? So let's say we have this example that we have time in minutes spent exercising in one day, and we measure that before an intervention. Then we have an intervention that where we encourage more exercise, and then we measure again time spent exercising after that intervention. And the objective is evaluate if time spent exercising is different before and after the intervention. And we have a sample size of 60. How do we do that? Well, we start by plotting our data, right? That's very common and what you should be doing at the beginning. You have time spent before the intervention and after the intervention. But does it really tell you where each subject started and then where it finished? Not really, right? Because at this point all the way down can be all the way up, or can all the way down can start, well, can end all the way down, right? So this gives us an idea of, okay, what we have at the beginning, what we have at the end, but the change that we want to see, it doesn't give you that idea. So it's better to plot this things, have a plot like this, right? So when we have, so for example, here's a plot of 8 subjects. I didn't include the 60 subjects because it's going to be a mess. It would be a mess, this graph. But then we can see that this subject that started all the way down here increased a little bit. But for example, one that started here almost at 105 went down, right? But here you have a better idea of what's happening. Over here, you don't have an idea of what happens before, how they change to after. So in this case, since we only have 2 points in this and for each subject, what we do, it's easy. We calculate a difference. In this case, what we do is do after minus before within subject, and then we plot this data. And that's what we're interested in, what happens with the difference in the subjects. So what do? We do calculate the sample mean of before, 96.74 minutes, the sample mean after, 99.74 minutes. And here what I'm going to be presenting is what happens if we analyze the data as if it were independent, so if they were not paired. So that would be the 2 sample t-test. And what happens if I use the pair t-test? The pair t-test takes into account that we have repetitions within a subject. The 2 sample t-test doesn't. It assumes that they're completely independent. So we calculate the mean after minus before, exactly the same. I have to do this more, like one map for there. And they're exactly the same, right? And that's expected. The same is we calculate the difference and then calculate the means, or then the means and then do the difference. Now, the 95% confidence intervals, they're different, right? So in this case, we have 0 when we have included in the confidence interval and do 2 sample t-test, and in the pair t-test, we don't have a 0. And when we do the difference between 2 means, and we want to know if there's a difference, the difference is 0 or not, that's the value that we're looking at sometimes in a confidence interval, right? So the conclusions, if we do a 2 sample t-test, assuming that they were independent, we can conclude there is a difference. No, that we cannot conclude that there's a difference in mean minutes between before and after treatment with 95% confidence. Whereas if we do a parity test, we can conclude with 95% confidence that on average, people exercise at least 1.91 minutes and at most 4 minutes. So we can see that the conclusions are different, right? Now, as I was saying, the 2 sample t-test assumes that the measures are independent, which is not our case. So it shouldn't be done. Yeah. Whereas a parity test, that's the way it should be done. Now, this is in terms of, well, minutes. In terms of practice, does 2 minutes make sense? 4 minutes make sense in practice to say, yeah, there was an improvement, that the intervention worked or not worked, that's a different story. But this is from a statistical point of view, you can see that the two have different conclusions. Yeah. Now, we have more explanation of how to analyze data when we have paired, and some seminars that Stat Central has given a while ago. One is this one by Nancy, and it's an analysis of pretest post-test data, and you can get it here if you want to have more information. There are other ways of analyzing paired data, and also there's this other seminar, paired data, that Peter also has. So you can have if you want more information. Now, what happens if we have groups or clusters with more than 2? So then we can have nested data, and when we have nested data, we have more than one measurement in each subject, and it can happen either we have a randomized an RCT, and then we have clusters. We create the clusters because sometimes it's easier to randomize to one cluster than the other. Let's say that we have hospitals, so we have an intervention in hospitals, so it's easier to randomize in a hospital, so give one treatment to one hospital, give another treatment to, well, or intervention to another hospital. Or we can have naturally occurring groups, that is, let's say, families, so those are naturally occurring groups, and we observe that, so the family can be a cluster, or also a person that has repetitions, that's another natural cluster, right? Examples of nested data, so we have players in teams, that's one level of nesting. Then we can have students in classrooms, and then classrooms in schools. Also, we can have patients in doctors in hospital, or several measures in a patient. Or we can have bananas, we can have over there a branch of bananas, right? That's how it's called, branch of bananas. That means that they're similar. When we have cluster, that means that they're similar within that group, or that's what we expect. Now, in this case, that's what we had before. We had at the beginning, we had 1 point, then we went to 2 points, that we have several points in one group, and you expect those to be more similar compared to the rest of the groups. So then an example, let's say that we have dragons, and we train those dragons to see if they're more intelligent or not, they become more intelligent or not. So we have data in those dragons. We have the body length and the dragon intelligence, that is called test score. We have 480 dragons, and they're measured in 8 mountain ranges. The research question, we want to know if there's an association between dragon intelligence and body length. A weird example, I know, but and I got the part of the data from this link. Now, when we have this type of data, we want to know if there's an association between 2 numerical variables. What do we start looking at? So we just do a scatter plot, right? So we have our Y variable here, our outcome variable, and our independent or explanatory variable here on the X-axis. So we want to see if there's a linear association in those 2 variables. So if we were to assume that they're independent, that there's no groups over there, what do we start doing? We can do a linear regression, where we have our test score. Sorry for the formula, but test score, if it's as an outcome and an independent variable, it's body length. Yeah, and that's what we want to see if there's an association. And in this linear regression, we have that our error, epsilon, has a normal distribution with mean 0 and variance. If we run a model like that, we end up having this outcome. Our beta 1 hat, so the estimate of our slope, is 0.555 with a standard error of 0.06. So then just with this, with a point estimate, we can say that for every unit change in body length, there is an average of 0.55 change in test score. But also we have to check the confidence interval, right? The confidence interval, in this case, when we're running a regression, also we're interested to see if 0 is in the confidence interval or not, to see 0 if it's flat or not. Our confidence interval does not include 0. So we are 95% confidence that it can go from 0.437 to 0.672. Now, okay, let's say that we do that, we don't assume anything. But, well, sorry, and then we feed, and this is the line. Yep. Now we think, well, what happens? We have 8 mountain ranges. So what happens if we start to see, okay, what is like, does mountain range have to do anything with all this? Does it have an influence in my relationship? So then we can plot the same scatter plot that we had before, but now by mountain range, well, with differentiating the mountain range by color. And we can see that, for example, the Bavarian, no, this is the southern, it's all the way over here. And then we have different mountain ranges in different places. So should we take that in the analysis or not? So then we also plot this just to see, okay, if we separate them by the mountain range, what do we have there, right? So we can see different things, this different plots. So then here we have, if we decided to go for a linear mixed model, this is an extra term that I would include. Now, my question is, I don't know if anyone wants to answer here for the 2 people that are present or online. Why would we go for a linear mixed model, including, in this case, a random intercept for mountain range and not a fixed effect for mountain range? Does anyone want to enter out? No one online? No?
No one online.
No one online? Okay.
Does the mountain range have a different impact on different dragons?
Well, it can be, yeah, but the thing is that here, our main interest is the relation between body length and test score,
Yeah.
right? And if we wanted to account for the variation by mountain range, that's when we include this random interest, right? So that's one reason. Another reason is we could assume that we have the 8 mountain ranges coming from, it's a sample from a bigger population of mountain ranges, and we're only measuring that. So that's another reason that, well, we would like to do that. Another one would be, we have 8 mountain ranges. If we were to include it as a fixed effect, then we would have to estimate 7 beta coefficients. So imagine if we had, in this case, we have 8 groups. If we had, sometimes you have 100 groups or 50 groups, you would need, if it's a fixed effect, you would need to estimate the number of groups minus 1. So it's several reasons why we would like to have this as a random intercept rather than as a, yes?
How many parameters do you have to estimate?
With this one, only the only the sigma, instead of so that's a good point. Only the sigma, right? So that's the thing here. Instead of estimating 7 effects, 7 beta coefficients, here we only need to estimate the sigma in this case. Yeah, and we're really not interested in that effect from like the relation between the mountain range and the outcome. Is just taking into account the variation. And we are assuming that the error that we had before the epsilon and the UI are independent. If we run that, now we have our estimate of a beta 0.033, 0.079, the standard error. So based on the point estimate, for every unit change in body length, there is a 0.033 change in mean test score. But if we now have the confidence interval now includes 0. So we cannot conclude there is association between dragon intelligence and body length. Yeah. Now, if we were to, well, if we did this random effects model, X effects model, this line would be this overall, using this beta 1 hash, this is my overall line, my mean line. But then each of the ranges, that's the idea with the random intercept, right? That we have an overall beta hat, and then for each one, we're going to add or subtract their corresponding random coefficient. Yeah. So if you see they're parallel, because I'm only changing the intercept, their slope with a different story, it's a different, you need to add more things in the regression line. Now we compare the results, linear regression, beta hats, different, very different. Standard error, in our linear regression, the standard error is smaller than in our linear mixed model. Confidence interval in a linear regression does not include 0. In the linear mixed model, it does. And the width, so the width is smaller in our linear regression than in the linear mixed model. And the conclusions, again, are different, right? Because with one, we can say that for every unit increase, there's another unit increase in the mean test score. With the linear mixed model, we cannot say there's a relationship. Yeah, so they're different. So you can be concluding different things based on a different model. So now, if cluster matters, it is expected that the observations be more similar within groups than between the groups, right? Usually, if you take a blood pressure in the same patient several times, it is expected that that blood pressure is going to be more similar within than compared to other subjects. Measurements within a group cluster cannot be considered independent. If, again, cluster matters, analysis should take into account that. And we saw that conclusions can be different if we don't take into account that. Now, when we have clusters, we have two sources of variance in the outcome, the within and the between cluster variance. And now the variance of our outcome in a linear regression, this is the one. And remember, these were the sigmas that we had from over here in a regression over here. So these are the sigmas that we have over here. So the variance of our outcome now include these two sigmas. Before, it only included the sigma that belonged to the epsilon. So we go back. So we need to take into account both sources of variance in the analysis. That's what we're doing when we're doing a linear mixed model. In the linear regression, we're not doing that. So generally, if clustering is not taken into account, and when it should, that standard errors are usually smaller, and that's what we saw in our regression example. The confidence intervals will be narrower, and that's what we saw. The test statistic, in this case, I didn't talk about p-values or test statistics, but a lot of people calculate p-values, use test statistics. So the test statistics will be larger, which implies smaller p-values, and that implies a risk of false positive error is increased. Yeah, and in our example, that's what happened, right? We concluded that something was significant with the linear model that doesn't take into account the clustering, whereas in the other one, we didn't conclude that. Now, we also have what is called the interclass correlation, measurement of how much more alike observations are within a cluster. And also there's the definition of proportion of total variance due to the clusters. If ICC is 1, that means that basically the observations within a group are providing the same information. If it's 0, they're providing different information. So if there's 0, then we can use linear models. We don't need to worry about it. But if it's closer to 1, then we have to use it more surely. Even if it's small, we should be using methods that take into account that. And in our example, that's the formula of ICC. If people are interested, there are different ICC formulas, depends on how many levels you have, how your model is. And here I will provide some instances of non-independence. We have nested structures. So here what we have is we have patients inside ambulance and then ambulance inside of departments. I think that is called in this paper. So that is a nested structure. But also we have cross structures where we have patients inside of ambulance, but also patients that belong to different health plans. So then it's a mixture. In the previous one, all these three belong to this one and did not belong to any other group. The same ambulance belonged to this department, but did not belong to group. Whereas in this example of cross structures, yes, they belong to this one, but this patient, some of these patients belong to one health plan, but others belong to another health plan. So it's crossed among all of them. So that's a different type of linear regression. Well, it's the same linear mixed model, but the structure of randomness, it's not just only the intercept, but you have to take that it's crossed, and then so it has to change. It's not exactly the same. In a way, I presented the simplest way for the linear mixed model. We also have longitudinal data. So when you measure people over time, so let's say here we have age, and we have males and females. And in this example was the distance between the teeth, I think the front teeth, for girls and for boys, and then we saw them throughout time. So in this case, when we have longitudinal data, then we have to take into account maybe correlation with respect to time. And that means that my observation with respect to the previous is more correlated than with respect to two previous ones, and then with respect to three previous ones, et cetera, et cetera. Spatial data also has to do with, well, as the number implies, something that has to do in space. So this was a paper that had to do with COVID-19 and something about vulnerability. So they did something, well, with respect to the areas in Australia. Now, what is the sample size that we have now when we have a cluster, when we have a group? Is it the total number of observations? Not necessarily, because they're providing, many of those observations are providing similar things. So it's not exactly the total number of observations. So is it the number of clusters? Also, well, we're giving us a little bit more information than just the number of clusters. So we have something that is observed versus effective sample size. The effective sample size depends on the degree of the within cluster correlation and the average cluster size. It's always better to have more clusters with few observations than few clusters with more observations per cluster. Because when you have more clusters with few observations, since those are said to be independent, you're providing more information. If you have two subjects with 100 observations, that's not giving you a lot of things, right? Where it's the opposite, then it's better. Now, disclaimer, examples here are very silly examples. I just took them from the web or simulated some data, but it's mainly an overview to show you that results can be different if you choose one method over the other. The assumptions needed for the methods were not mentioned, so that's a different thing, that's a different subject. And also sample size was not discussed in the examples, but it's just sort of a big thing here. Thank you was short, and if you were interested in mixed effects model or something, then there's some reference there. Some are more technical than others are applied. So then I'm happy to take questions if there are questions. No one? No one, either everybody's left or
Here we go. Can you provide an example of when you would need to model random slopes? Are there power or sample size considerations?
so first the example when it's a random slope, and then power and sample size consideration.
Yeah.
Okay, so yeah, they're asking an example when random slope. So back in this example, the dragons, I only use the random intercept, but if you go here, maybe you could say that each one has a different slope, right? You could argue that each one could have a different slope. this, I don't know, might have a slope of 0, whereas this does not have a slope of 0. So in this example, you could add a random slope by mountain range and check if that is relevant or not. There are tests to check if the random, like the variance of that random slope is relevant or not. That would be the answer for that. Now, power and sample size. When you have power and sample size, when you're dealing with random effects and linear mixed models, usually what you do is deal with simulations. You have to come up with simulations. What is the beta coefficient that you expect? What are the things that you expect? So then precisely, I don't like, it's different to what we have if we were dealing with linear. It's more straightforward when you're dealing with linear regression than when you're dealing with linear mixed models, because then you have to do more simulations. So yeah, it's a different thing on its own. No one else?
Can you explain if heterogeneity tests within this?
Again, what?
Can you explain if heterogeneity tests within mountain ranges or other factors are similar concept with cluster analysis?
Well, heterogeneity test, in that case, if there's heterogeneity test, you're checking if there's some variability in each of the, well, if there's different, the variance is different in each group. In this case, the linear mixed model takes into account this variability to see if there's an association in the variables that you want to see, the association. And
Does that answer?
if that answers the question. No one else? Okay. No more questions? Hopefully it was not too boring. So thank you.